Let's talk about the second big topic in chapter 5.4. You could call it part B or part 2. The textbook doesn't really say here's a part dividing line, but it's about the average value of a function, and the first question might be, why should we care? Well, let's suppose you have a long, thin lake, so you can treat it as kind of one-dimensional, and it has an oil spill on it, and someone has mapped the oil concentration function, so at one end of the lake there's more oil per square meter, and at the other end of the lake there's less oil per square meter. Then if you just let that oil sit and let it spread out, eventually when it all gets evened out, it will even out at a concentration that's equal to the current average concentration, the current average value of that function, as long as none of it evaporates or sinks or gets eaten by wildlife or anything. So that's one place we might care about the average value of a function. Another one, suppose someone took a medicine and initially it was mostly in their stomach, not really in their blood, and then it went up, the concentration in their blood went up, and then came back down. You might want to ask, what was their kind of average exposure to the medicine? In this case, the medicine, we hope you have some exposure to it, otherwise you wouldn't take it, right? So you might want to say, well, it kind of averaged out at what? Maybe 100 milligrams per liter across those 48 hours. So those are some applied problems where we want to take the average. We might also care about kind of the average velocity, since average velocity is related to slope of a secant line and all that good stuff from Calc 1. But let's go talk about how we're actually going to do this now that we have some motivation for it. When we're exploring a concept, it's often helpful to start with really simple examples. So here I have a really simple example for us. If you have f of x equals 3 all the time, never not 3, and you wanted to know what's the average value of that function on the x interval 0 to 5, what would you say? Probably 3, right? So just to establish kind of a baseline idea of average. How about this function? What would you say is the average value of this function where it's 3 from 0 to 4, and then it's 11 from 4 to 5? So take a sec to think about that. So one answer might be, well, it's 3 and then it's 11, and I know how to take the average in stats class. I just add the stuff and divide by the number of things I added. That would be what, 14 over 2, which would be 7. Do you agree that the average of those is 7? Well, it's at 3 longer than it's at 11, so maybe we want to say that the 3 is kind of pulling the average down toward itself, away from kind of middle between 11 and 3. So we'll say probably not. It spends longer at 3 than at 11. So how can we compensate or account for the fact that it spends longer at a y value of 3 than at a y value of 11? Well, if we took a stats point of view, we might say, let's kind of sample it. We might say it's at 3, 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 and then it's at 11, right? So we might say, what if we sampled it here, 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 and here? We'd have a 3, a 3, a 3, a 3, and then an 11. And we could say, okay, take the average of all those and divide by 5. Might be kind of reasonable. What's the calculus equivalent of that? Well, in calculus, we like to think about total area under the curve or total area so far. So we might say that first 3 is actually kind of a box of height 3 and width 1. And then the next box goes from 1 to 2 and also has height 3. And then the next box goes like that, and then the next box like that. Then the next box goes up to 11 and has a width of 1. So we could write 3 times 1 minus 0 for that first box. plus a height of 3 times 2 minus 1 plus a height of 3 times 3 minus 2 plus a height of 3 times 4 minus 3 plus a height of 11 times 5 minus 4. You might wonder, why am I writing this subtraction every single time? Can't I just write a width of 1? And I could, but I really like to consider the case when my boxes might not all have the same width. That happens fairly often in applied problems. So it's a question of, do I want to take a shortcut now that doesn't generalize later, or do I want to practice a method now that ends up working well later, even if it takes me a little more thinking this time? So do you agree that this is basically 3 plus 3 plus 3 plus 3 plus 11, like we wrote there, but we haven't divided by 5 yet? You could say let's divide by 5 because I added up 5 things. You could say let's divide by 5 because my total width was 5. So you could say divide by 5 minus 0, which is also called 5. Both of those are good things to think of. So this 5 minus 0 is our total width. Now, the actual answer to this problem isn't all that important. We'll just write it down here real quick. It's 23 over 5, which is 4.6, which is a fair bit lower than 7. But really the main idea we're getting here is break it into pieces, add up the pieces, and then divide by the total stuff you did, whether that's data points or total width. Could you say that this is a weighted average? Weighted average is usually the data points times kind of the importance of each data point, and then divide by the total weight. So I'd say this is a weighted average. And it's weighted by box widths. So next we'll go talk about this in a more general setting where we have a curve or something.